In this video, we are going to learn how to solve for the optimal two-part tariff when we have two customer types. Let's suppose that a golf course charges a monthly membership fee M plus a separate price for each round of golf P. The golf course serves two types of members with different demands for rounds of golf. Local members have a demand described by Q equals 20 minus P, and non-local members have a demand described by 16 minus P. In this case, P is the price for a round of golf in dollars, and Q is the number of rounds of golf per individual. The golf course has determined that there are 10 potential local members and 10 potential non-local members. Their marginal cost for a round of golf is $4, and they also have no fixed costs. On to the question we're trying to answer. If the golf course is not able to charge different fees to locals and non-locals, then what price per round and membership fee should they charge to maximize their profit? What do we need to know to answer this question? We need the demand curves for each market. We also need the number of buyers in each market. And finally, we need information about the firm's total cost or marginal cost. How should we go about solving this question? There's no easy way to state this, so I'm going to be pretty general here and say we need a graph, an accurate graph, and we also need a basic understanding of the optimal two-part tariff. So let's solve this and along the way talk about the sort of optimal method for solving it. First thing we need to do is sketch the two demand curves. Those demand curves are QL equals 20 minus P and QN equals 16 minus P. I'm also going to sketch the marginal cost, which is $4, and then we'll talk about all the different shapes in my graph after that. So if we sketch the non-local market, that's the orange line on the left-hand side, notice that the demand curve runs from 16 to 16. And I have carefully sort of labeled those intercept values. Notice that the local market, which is the red line, runs from 20 to 20. And I've also put a nice horizontal line in at the $4 marginal cost. So there's our graph. I also said we needed a basic understanding of the optimal two-part tariff. So I want you to remember that the optimal price, the per unit price, or in this case, per round price, is going to be something above marginal cost. If this was a single type, if we just had locals or non-locals, then the optimal price is marginal cost. But once you have two types, the optimal price becomes something above marginal cost. So that's why in my graph you see I've sort of labeled a P, an optimal price. I'm going to highlight that for you. P. And I've indicated that at this per round price of golf, the number of rounds demanded by non-locals is 16 minus P, that's coming from their demand curve. And the number of rounds demanded by locals is 20 minus P, that's coming from their demand curve. What else can we say? We know the optimal price has to be above marginal cost. We also know that the optimal membership fee is what I call the would-be consumer surplus of the low demand group. So we look at our graphs, we observe that our non-locals, the orange line, are our low demand group because their willingness to pay tops out at 16 and the willingness to pay of locals tops out at 20. So our low demand group is the non-local group. And it says, again, just read it again, membership fee is the would-be consumer surplus of this group. Well, if we set the entry fee if we set the per round price of golf equal to P, then the would-be consumer surplus is this green shaded triangle, the area below demand and above price in the non-local market. Just so we're clear, these membership fees are pure profit. There are 20 potential customers here. If we collect 20 membership fees, then we have 20 times this green triangle as our profit. But that's not the whole story. There's actually more profit than just that. It turns out that from each non-local member, that's the orange line, the golf course is going to earn additional profit of price minus marginal cost times times Q, where Q is 16 minus P, and that's coming from the non-local demand curve here. Well, what is price minus marginal cost times 16 minus P? That's the orange shaded rectangle. So far we have this, we're sort of building this idea of what is profit under a two-part tariff. Well, we're going to collect 20 green triangles, and then we're going to collect 10 orange rectangles from our non-locals. But then we're also going to collect something from our locals. From each local member, the golf course is going to get additional profit of price minus marginal cost times quantity, where this quantity is 20 minus P. So if we look at our red line, our demand for locals, we can see that this red rectangle is profit earned from each local member, because where is this coming from? I think it's really important that we recognize this. This red rectangle is coming from the fact that price for a round of golf exceeds marginal cost. So we know that each person is going to demand 20 minus P rounds of golf. We multiply that quantity by how much price exceeds marginal cost by, price minus 4, to figure out how much extra profit we're earning from each local. So we get 20 green triangles, we get 10 orange rectangles, and we get 10 red rectangles. This is why earlier I said we needed a graph and a good understanding of the optimal two-part tariff. Without both of those parts, you're completely adrift in the process of solving this question. So let's wrap up everything we've said so far. We know there are 20 potential members, 10 are local and 10 are non-local. As a result, as a sort of baseline starting point, we could say that profit is 20 times the green plus 10 times orange, that rectangle, plus 10 times red. So green is profit from membership fees, orange is profit from charging a price above marginal cost to non-locals, red is profit from charging a price above marginal cost to locals. Now that we have a basic understanding of that optimal two-part tariff and how to write down the profit function, we need to update it to include the details of the question. In particular, we could determine the area of the green triangle as 1/2 base times height, where the base is 16 minus P, or the height is 16 minus P, and the base is 16 minus P as well, just so we're clear on where those are coming from. The height is 16 minus P, where P is what we're solving for, the profit maximizing price per round of golf. And the length of the base is also 16 minus P, where that's coming from the demand curve. That's green. We can also find the area of orange. Orange is a rectangle. It has area of base times height. I'm going to erase my annotations here. The height of this rectangle is P minus 4. And the length of the base is 16 minus P. Finally, we have our red shaded rectangle. Notice that the height of that rectangle is also P minus 4, and the length of the base is 20 minus P. Just so we're clear, where does that 20 minus P come from? We've sort of picked this P that we're searching for, and we know that at a price of P, quantity demanded, in the local market is 20 minus P, and we know that because that's the structure of the demand curve. It's Q equals 20 minus P. Next, we need to substitute our green, orange, and red formulas into that profit function and do a little bit of simplification. So we have that profit, let me try that again, profit is equal to 20 times 1/2 16 minus P times 16 minus P plus 10 times orange, which is P minus 4 times 16 minus P, plus 10 times red, which is p minus 4 times 20 minus p. So far I just plugged in what I know. Now I want to try and simplify this thing. I want you to recognize that this is not a fun thing to simplify. I'm going to start with this 20 and 1/2. So the 20 and the 1/2 becomes a 10. So I'll rewrite this as 10. I'll also note that I have a 16 squared, or sorry, 16 minus p is all squared. So I'll write that as 16 minus p squared. And then, so that was this whole term here that I just sort of dealt with. Now I want to deal with the other two terms. It might not look like they can be combined, but they actually can because they both have a 10 times p minus 4 in front of them. So I can factor that out, plus 10 times p minus 4. Factoring it out, I have a 16 minus p plus 20 minus p. Whew, we're getting somewhere. We're going to do one last thing. Notice that both of these terms have a 10 in front of them. So I'm going to factor that all the way out. And I'm going to write profit as 10 times 16 minus p all squared plus p minus 4 times whatever all this is simplified. Well, that's 36 minus 2p. So it's not pretty, it's still ugly, but at least it's got fewer terms in it. We can call this equation 4, and this is really what we're looking for. We did a lot of talking. We've been talking for almost 10 minutes already, at least. And all of that was just to write down the function that we needed to maximize. So it's a lot of upfront work where we have to sketch these lines, we have to label the relevant areas, and we have to conceptualize what a two-part tariff is, all to get to this point. So we have our profit function, and now we need to apply the first order conditions for our maximum. That means we need to take the derivative with respect to p and set it equal to 0. Now, depending on your calculus skills, you may prefer to try and multiply this whole horrible profit thing out. I know that I will make many errors if I try to do that. Instead, I'm going to use more complicated derivative methodology, particularly the chain rule and the product rule, to find the derivative of this profit function. If you don't like that, I apologize. It's the only way I know I can do it to get it right. You can revisit this problem on your own and try and multiply out before differentiating. So we're going to take the derivative. The first thing I'm going to note here is that there's a 10 in front of everything. So I'm going to write that 10 down. It's multiplied by all the terms. I know it's still going to be hanging around when I'm done. And then I see I want to differentiate 16 minus p all squared. To do that, I need to use the chain rule, which says I'm going to differentiate the outside function and then multiply by the derivative of the inside function. So I bring down the 2, the square term. I leave the inside function 16 minus p alone, and I reduce the power by 1. So it goes from 2 to 1. And then I multiply that derivative of the outside function by the derivative of 16 minus p. Well, that derivative is negative 1. Okay, so that was the chain rule that I just had to do. Now I have to use the product rule to differentiate all of this because I have two functions multiplied together. The product rule says first we take the derivative of the first function, p minus 4, so the derivative of that is 1, and we multiply it by the second function, 36 minus 2p. Then we add the opposite. What do I mean by the opposite? I mean, now I'm going to take the derivative of the second function, 36 minus 2p, that derivative is negative 2, and I'm going to multiply it by the first function, not the derivative, but the first function itself. Phew, and I set this whole thing equal to 0. So notice I had used the chain rule and the product rule, which I know most of you are probably very unhappy to see. From here, we should be able to simplify and solve for p. It's not going to be fun, but we can do it. So first things first, I can just get rid of this 10, multiply both sides by 1 over 10, and it's gone. Then I want to start simplifying a little bit. So I'm going to multiply 16 by 2, and I get 32, and then 2 times negative p is negative 2p, but then I notice all of this is multiplied by negative 1, so I'm going to change this to a negative 32 and this to a plus 2p. So that was me simplifying this first term. Then I have, let's see, plus 36 minus 2p. That one was easy. I have to deal with this negative sign. Negative 2p plus 8 all equals 0. So let's collect terms. What am I going to collect? Well, I'm going to highlight all the p's because that's really going to help me. I have 2p minus another 2p. Clearly, that leaves me with just minus 2p, which I'm going to shuffle over to the other side of the equation and call 2p. Now I need to deal with these constants. 36 minus 32 is 4, and 4 plus 8 is 12. Phew, we're almost there. We divide both sides by 2, and we get that the optimal per unit price for a round of golf is $6. So we've solved. If we're looking at our picture up top here, we solved for that P, it's 6. But we're not done yet. So here's everything that we know. We have our green shaded region, our orange shaded region, our red shaded region, as well as our profit function. From that profit function, we found the optimal per round price of golf was $6. The last thing we need to do is to find that membership fee. Just as a reminder, the optimal membership fee is the would-be consumer surplus from the low demand market, which is our non-locals. In this case, we've already identified that the green shaded triangle is the membership fee. So we're just going to substitute price equals 6 into that green shaded triangle formula, equation 1, and we should have our membership fee. So we have M is equal to 1/2 16 minus 6 times 16 minus 6. Simplifying a little, we have 1/2 times 10, which is of course $50. So with a lot of work, we finally got there. The solution to this problem is that the golf course should charge a monthly membership fee of $50. That's equal to that green shaded region, and a price of $6 per round of golf played. If I wanted to make this video longer than it already was, I could go back and I could figure exactly how much profit our firm was earning under this two-part tariff scheme, but I am not going to do that.